Thank you very much. So this is a great honor for me to speak at this conference on the legacy of John Tate. And like many of you in this room, I met personally John Tate only once. And it was in Italy, in the South Tyrolean region. And John Tate was attracted there for a conference and also by his former student, Bernard Work, was his student, but he was older than his supervisor. And well, I had the nice and great opportunity to meet John Tate there. So this is a very nice memory. So I will, as Björn Poonen said, there are many aspects of the Tate conjecture. He spoke on the origin, on the deep connection with the arithmetic of function fields, and also on computational aspects. So I will concentrate on more structural aspects. So this is a statement of the Tate conjecture. So it deals with a talc homology of, let's say, smooth projective or proper varieties over a finitely generated field, K. X bar is the extension of scalar to K bar of the variety X. And the talc homology is a representation of the absolute Galois group of K. And well, the Tate class is a Galois invariant in talc homology in degree I, twisted by n. And this exists only if I is 2n, in fact. So by curly Tn of x, I denote the space, the QL space of Tate classes. And the Tate conjecture is claims that the cycle class map of, well, you could put Zn as Björn did, or the Chow group. This is the same conjecture. In degree n, tensor with QL, which maps to Tn, is surjective. So the first topic I would like to discuss is the group-theoretic formulation. So firstly, what does it mean? It means you have a Galois action, you have the image of a Galois in the automorphism of the cohomology, and you can look at the Zariski closure of this group. So this is a linear algebraic group, a subgroup of a group. So I denote it by HL here. Oh, sorry. Subgroup of GL. And via the QNet formula, which identifies the cohomology of the product of X bar with the tensor product of the cohomology of X bar, Tate classes correspond to GL, to HL invariant. I'm sorry, there is a typo here. This is HL invariant mixed tensors on the cohomology. So I would like to reformulate first Tate's conjecture in terms of HL. So there are two subtle issues. The first issue is that, well, this group HL, is it the biggest subgroup of GL which fixes its invariant tensor? This is not clear, a priori.
I mean, do you mean HL invariant mixed tensors?
Yeah, you said that.
Oh,
Yes, yes. This is a typo, yes. Sorry. This should be HL here. So, and the second issue is what if you want to compare? So, in the Tate conjecture, there are the algebraic cycles and there are the Tate classes. So, what is the counterpart of HL on the side of algebraic classes? And what can be said about the analog of this issue 1 for this other algebraic group? So but I would like to discuss this matter, this issue 1, in a more general framework. And this is in the context of observability, which I will define at the end of this slide. So now let G be any linear algebraic group over a field of characteristic 0 for simplicity. And let be H a closed linear subgroup, algebraic subgroup. And by representation of H or representation of G, I will mean a finite dimensional rational F-linear representation. So now H come with another group, which I denote by H dash, which is the largest subgroup which fixes the H invariance in every G representation. So of course, H dash contains H, but it's not clear that they are equal. And in fact, this is one possible definition of observability, which is an older theory which goes back maybe to the 60s, which is a little bit forgotten, maybe. H, a subgroup of G is called observable if H dash is H. So by definition, those observable subgroups are those which are detected by invariant theory. That's the reason they are called observable. So now there are a lot of equivalent conditions, which makes this theory rather rich and useful. And these conditions are due to many authors. In fact, the authors I mentioned here did the case where the ground field F is algebraically closed, but it works in general, in fact. So the first condition 0 is that H is observable in G, so H is equal to H dash. The first criterion is that every representation of H is contained in a representation of G. By this, I mean that it's a restriction to H of a representation of G. The second condition, which is equivalent, but which a priori seems weaker, is that every character, so every one-dimensional representation of H, occurs in a representation of G. And the third condition, the third criterion, which is the most powerful because it seems to be even weaker, but is equivalent, is that for every character of H already occurring in a representation of G, its inverse also occurs in a representation of G. And there are a fourth condition, which is also rather striking, is that H is an isotropic group of some element in some representation of G. And the fifth condition, which is more geometric, is that the homogeneous space G over H is a quasi-affine variety, which means it's open in some affine F variety. So let me discuss some first a non-example. A Borel subgroup of a reductive group, when it is not a torus, is never observable. For instance, if G is SL2, and if you take the standard representation of SL2, then by restriction to a Borel subgroup, it becomes an extension of a character by its inverse. And the first character is not contained in a SL2 representation. And more generally, for a Borel subgroup of a reductive group, Borel subgroup H of a reductive group G, H dash is G. So now an example, any reductive subgroup is observable. This is because, any subrepresentation is a direct summand. And another less trivial example is that any normal subgroup is observable, and in fact, conversely, if you have a subgroup H in G, which is observable, and if you know that for any G representation V, the H invariant form a G-stable space, then H is normal in G. This is a very useful normality criterion, in fact, due to NO high and so on. So now let us go back to our example where GL was the automorphic group of P-adic cohomology of X bar, where V is the representation the étale cohomology of X bar, and viewed as a GK module, and where HL is the Zariski closure of the image of GK. Here, the field of coefficient F is QL. Then there is this theorem about the image of Galois and its Zariski closure HL, is that it cannot be any subgroup of GL. This is always an observable subgroup. So I published this thing very recently, but the main case, the most difficult case, relies on argument of Ben Monen. So this is, in fact, very much inspired by Monen paper. So that's why I put his name here. So let me sketch a proof of, in the most typical case, in characteristic 0. There are 4 steps. First, one uses some specialization argument à la serre, so using the fact that number fields are Hilbertian, to reduce to the case that the field K, the ground field K, X is defined over K, is a number field. So this is some kind of Hilbert irreducibility in the case of infinite Galois extension. And then, by a naive restriction of scalars, you can take K to be Q. And this is essential in the next argument, which is due to in the step 3, which is due to Monen. But now let us use in this setting the third criterion of observability. The third criterion says that you consider a character of HL, but such character which will come from a character of the Galois group over Q, absolute Galois group of Q, to, in fact, to ZL cross. Okay. And such character, which occur in the twisted cohomology group V of some power of X, we have to show that its inverse has the same property. And for this, it suffices to show that actually, up to a finite character, this chi is just an integral power of the cyclotomic character. And one may assume that it has infinite order, otherwise this is trivial. So the main step, which is due to Monen, is that by the Kronecker-Weber theorem, the extension, which I denote by L of Q, which corresponds to the kernel of this character, which is the infinite extension of Q, contains the cyclotomic ZL extension, which I denote by Q infinity of Q, with a finite index. And since L is totally ramified in this cyclotomic ZL extension, the inertia inside the Galois group of L over Q at a prime above L is always open. So now the main point is that V is of geometric origin, and so by P-adic Hodge theory, by Falting's theorem, Tate's theorem for Abelian varieties, it is Hodge-Tate. And so it is known that a sub-representation of Hodge-Tate representation is still Hodge-Tate, and so chi is a Hodge-Tate character. And this implies that there is an open subgroup, J, of the inertia, I, such that chi restricted to J is the integral power of the cyclotomic character. This is typical of a Hodge-Tate character. In general, it would be any power to some P-adic integer of the cyclotomic integer. But here is the integral power of cyclotomic. And so we are done. Well, I should say that this theorem is valid for any finitely generated field K, even in characteristic P. This is also valid beyond the case of projective smooth varieties. This is valid for any motif, in fact, even mixed motifs. This is a quite general fact that the Zariski closure of the image of Galois, the cohomology of something which comes from geometry, is always observable. So, but now let us turn to the second issue and to say something about the side of algebraic classes. So a group-theoretic formulation should involve some group which fixes algebraic classes. So for simplicity, I will discuss here only the case when the characteristic is 0. And even to be even more explicit, that algebraic closure of K lies in C. Then at disposal, we have Artin comparison theorem, which gives a Q structure, rational structure, namely the Betti cohomology of XC on the étal cohomology. So the étal cohomology with QL coefficient is just H Betti of XC tensor QL. Now one can consider the subgroup, which I denote by G edge of X, of the group of automorphism, linear automorphism of the Betti cohomology, which fix all algebraic classes among all mixed tensors on the Betti cohomology of XC. Equivalently, which fix all algebraic classes and all powers of X. There are some issues with this group, which is not so well behaved. For instance, if you have a product of smooth projective varieties, X and Y, it's not clear that the image, so there is a natural homomorphism between this group G edge of the product towards the group G edge of X. It's not clear that it is surjective. It might be that there has some exceptional algebraic class on the product, which give a constraint on the group on the project, so that when you project on the G edge of X, you get something smaller than what you get when you only consider algebraic classes on the powers of X. And the second related issue is that it's not clear that you have this observability phenomenon. It's not clear that algebraic classes are the only G edge of X invariant tensors. So the remedy is rather straightforward. It's to define the Motivic Galois group of X as an intersection over all projective smooth Y over K of the image of the group G edge, the product, towards the G edge of X. In fact, this is not this is not the way I see these groups. There are other formulations, but the invariant under this group in the cohomology of the powers of X are called motivated, and they can be described in a number of different ways. For instance, you have a theory of mixed motif by Nori and also by Ayub, and so which is a Tanakian category, and characteristic 0, which works. So you get some Tannakian group, and their invariants are exactly the motivated cycles in the pure case. So all existing working theory of the Motivic Galois groups and Tannakian category of motifs in characteristic 0 give the same result. But the constructions are highly different, really different, and it's highly non-trivial to prove that they give the same result. But just to insist on the fact that they are not, it's not just a bunch of competing different theories, they give the same result. Just the picture is richer because the constructions are completely different. So now we have this group, and this is a Tannakian group of the Tannakian group of motifs generated by X, and this is a reductive, hence observable subgroup of GL of the Betti homology of X. Now the algebraic classes are motivated by construction. It's not clear, the converse is not clear, and in fact, it's just the content of the Grothendieck standard conjecture in characteristic 0. On the other hand, the motivated class are Tate classes, and so this leads to a following Motivic variant of the Tate conjecture, which is slightly weaker than the Tate conjecture, but which extends to the mixed motif setting. So this is a conjecture which I denote with primes, so slightly modified, so Motivic Tate conjecture. Tate class on X are just a QL combination of motivated classes. And since Tate class on X are the HL invariant mixed tensor, we approach a solution of our initial problem to give a group-theoretic reformulation, maybe not of T of X, of the conjecture T of X, but at least of T dash of X. So this is what I'm now saying. So the fact that the Zariski closure of the image of Galois in étale cohomology is always observable, plus the fact that the Motivic Galois group in characteristic 0 is reductive, implies the following corollary, which is a variant of a theorem, strengthening of a theorem by Monen. So in characteristic 0, the Tate conjecture, the modified, so the Motivic Tate conjecture for all powers of M is equivalent to the equality between the group HL, so Zariski closure of the image of Galois, and the extension of scalars to QL of the Motivic Galois group. And furthermore, it implies the semi-simplicity of the Galois representation, which is a new point. Before, it was known that the Tate conjecture plus this partial semi-simplicity, which was denoted by S of X in the previous talk, implies a full semi-simplicity. But here, the Tate conjecture is enough to, about invariant, about the Tate class, is enough to imply semi-simplicity of the Galois representation in characteristic 0. This semi-simplicity was a conjecture by Grothendieck, Serre, and Tate. Well, it is attributed to these three authors. I don't know who wrote it first. Of course, in characteristic P, this should be the same, but it's not known. Still open. And what is missing is reductivity of the Motivic Galois group, which is not known in characteristic P. So let me now address a question which is very frequently asked. What is the relation between the Hodge conjecture and the Tate conjecture? Is there any logical sense? So let me again take a field case, finitely generated over Q, and K bar, it's algebraic closure in C. So the Hodge class is something in the Betic homology, twisted Betic homology, intersected with the 0, part in the Hodge decomposition of the complexification of the Betic homology. And I denote by Hn of x, the set of Hodge class in H2n of xq twisted by n. Here in Betic homology, the twist by n is just a multiplication by 2I pi to the n, and you shift the Hodge filtration by n also. Okay, the Hodge conjecture looks very similar to the Tate conjecture. It has a cycle class map from the Chow group. Here there is no QL. And I should have put a Q here instead. This is a typo. A Q is missing. And so towards the Hodge classes, should be surjective. And how to reformulate this in group-theoretic terms? So Hodge structure, the Hodge structure of X or X bar is equivalent to morphism between so-called Deligne group, which is just a restriction of scalar à la veil from C to R of the multiplicative group towards the Betic homology with real coefficient. So this is an observation by Deligne, in fact. But the Mumford-Tate group is just the smallest closed subgroup of the linear of the rational Betic homology, which contains the image of mu. Remarks that I don't say that it's the Zariski closure of the image of U, because it's not clear that the Zariski closure of the image of mu is a group. And in fact, it's not in general. So this Mumford-Tate group, which was introduced by Mumford and Tate in a paper in a slightly different way, turns out to be a connected reductive group, and the Hodge class is exactly the same as MT of X invariant mixed tensor on the Betic homology. So now every motivated class is Hodge. It's also Tate. So hence the Mumford-Tate group is contained in the Motivic Galois group of X. So the Motivic variant of the Hodge conjecture, which I denote by H of X dash, so this is a weakening of the, but it has the advantage of extending to all mixed motifs, is that the Mumford-Tate group is equal to the Motivic Galois group of X bar. By the way, whereas the Hodge conjecture, there are not so many general results about the Hodge conjecture, but this apparently slight modification can be much more approachable. In fact, it can be proved for all Abelian varieties. This weakened Hodge conjecture. If X is an Abelian variety, this is true. Well, this is a weakening, so the Hodge conjecture implies this Motivic version. But now, if you put together the fact that motivated class are both Hodge and Tate, then, or if you prefer, if you combine the conjecture, the Motivic conjecture, Hodge and Tate conjecture, you are led to this Mumford-Tate conjecture, which relates directly Hodge structure to Galois representation, saying that the Mumford-Tate group, so now there is no motif, no Motivic Galois group, the Mumford-Tate group of X, when you extend the scalars to QL, should be exactly the connected component of identity of this group HL, of the Zariski closure of the image of Galois. The connected component of identity is there because, of course, I I consider on the left-hand side. The left-hand side depends only on x bar, so k is not important. But the drawback of this conjecture is that now there is no obvious inclusion in whatever direction. So both groups are maybe more easily accessible than the Motivic Galois group, but to show an equality when you don't know any inclusion might be difficult. So there is not only there is no known logical implication between Hodge and Tate, but if you, well, this lack of relation is pictured in the fact that, well, there is no inclusion a priori in whatever sense. And already to prove an inclusion would be very nice. So let me now speak about the Tate conjecture and another classical conjecture, the period conjecture. I put it in period conjectures because I will discuss the classical Grothendieck period conjecture for classical periods, and then I turn to the L-adic version or P-adic version. So now I specialize to the case where K is a number field. K bar is already embedded in C in this talk. I look at X, a projective smooth variety. I consider not only the Betti cohomology of X, but also the Durham cohomology, constructed in terms of algebraic differential forms. And they are related by the period isomorphism. This is essentially the integration of the differential form of the cycles, which I denote by this pi. So between Durham, twisted, with coefficient in C, and Betti, with coefficient in C. So this is a vector space over K. This is a vector space over Q. And if you take basis, you get a matrix, invertible matrix with complex coefficients, which are called the periods of X. Now, a Grothendieck or Durham-Betti class is a class maybe in Durham cohomology, here, which so that the period isomorphism send it to something rational here with respect to Betti. So it has a double rationality property over Durham and also over Betti. I denote by curly G the Grothendieck classes in cohomology of X. And the weak form, the Grothendieck period conjecture, looks very similar to the Tate conjecture or the Hodge conjecture, denoted by Gx. That's the cycle class map from the Chow group with scalar standard to Q to the Grothendieck classes is surjective. And a stronger form of it is that this says something about the transcendence degree of the periods of X, and this should be exactly the dimension of the Motivic Galois group of X. Now, let us look at the P-adic case. Well, in this talk, P is equal to L. In fact, this is related to it will be related to the Tate conjecture, where there is an L. So, but since I will use P-adic Hodge theory, it's not usual to speak about L-adic Hodge theory. So I switch to P. So I need to fix an extra datum, which is an embedding of K bar into QP bar. Okay, let us fix it. Then when you have this, you can combine Artin comparison theorem, which relates the Betti cohomology to the P-adic et al. Cohomology, and the P-adic et al. Comparison theorem of Fontaine, Faltings, and many other people, which relates the P-adic et al. Cohomology to the Durham cohomology. But now the coefficients are not C, not CP. They are in B Durham, this Fontaine ring of periods. And so so I combine both. So the p-adic et al. Cohomology disappear here, and this is a p-adic period isomorphism between which relates de Rham cohomology and Betti cohomology, okay, with cohesion in B de Rham, given by p-adic Hodge theorem. So one can define similarly the p-adic Grothendieck classes. These are classes which are rational both on the de Rham side and both on the Betti side. And in the late 80s, Fontaine asked the question, can one make the analogous statement as a p-adic period conjecture, the cycle class map, so group tensor Q, to this p-adic Grothendieck class is surjective? Or in even stronger form, can one expect that the transcendence degree over Q of the p-adic periods of X is exactly the dimension of the Motivic Galois group, as one expects in the complex case? So soon after, I answer the Fontaine's question in the negative. In fact, the answer may be positive, but may be negative. And this depends essentially on the choice of iota p, the embedding of k bar into qp bar. For instance, if you take an elliptic curve over Q, such that if you extend the scalar to Qp, you get a Tate curve. And if, moreover, the image of Galois is the full group GL2 of Zp, and there exists some such curve, for instance, the modular curve x0 of 11 for p equals 11, then you can construct two embeddings of Q bar in Qp bar, iota p and iota p dash, for which, for one embedding, the transcendence degree of the iota p periods is the dimension of the Motivic Galois group, is 4 in this case. Motivic Galois group is GL2 in this case. And for the other one, is less than 3. So this looks very strange, and Fontaine was very disappointed by this. But fortunately, there is good news that, in fact, he says, okay, that's wrong, but what if iota p is general, sufficiently general? And in fact, there is this theorem. If you assume that iota p is sufficiently general, which is a notion which is independent of x, it can be defined in an absolute way. There are some iota p's, and many of them. Then the Tate conjecture for all powers of x implies this p-adic Grothendieck period conjecture for all powers of M, and also with the strong form about transcendence degree of the p-adic period. So the moral is that, yes, but it's even better than in the complex case, because here this is a theorem. In the complex case, it's a widely inaccessible conjecture. So how come that one can prove something in the p-adic case, which is totally inaccessible in the complex case? Well, the point is that one has a period torsor, P of x, under the Motivic Galois group, and this p-adic, so classically, over when k bar is in C, this period morphism gives you a canonical complex point of the period torsor. Here, when you choose iota p, you have this p-adic period isomorphism, which defines a B de Rham point of P of x. And the issue is whether this point is generic or not. And one can prove that under the Tate conjecture, one can, maybe it is not generic, but one can modify iota p. There is the image of Galois is big enough, and use a kind of bare type argument. One can prove that one can always achieve by modifying iota p by action of Galois, that, in fact, well, the point defined by the p-adic period is generic in the period torsor. So this is so the fact that the p-adic situation can be handled comes from the fact that you have much more flexibility in the embedding of k-bar into qp bar. Okay, to finish, I would like to mention another topic, which is the Anabelian analog of the Tate conjecture. So here, X is a smooth, geometrically connected variety over a finitely generated field, but I don't assume that X is projective or proper. I will assume, for simplicity here, that K is of characteristic 0, but maybe not necessary. Now, QL local system may be reducible for simplicity, which I denote on X bar, which I denote by V bar, is said to be of geometric origin if when you restrict it to some dense open subset U, it is a direct factor of some higher cohomology for some proper smooth map from some Y to U. So it is a Motivic origin or geometric origin. Okay. So now the group J, the absolute Galois group of K, acts on QL local system on X bar, and the fixed points are just the local system on X. And one has this nice conjecture, which is a kind of Anabelian variant of the Tate conjecture, but under a strong assumption. Consider a local QL local system on X, but you assume that when you extend scalars to K bar, then the local system on X bar is irreducible. Then the conjecture is that not V itself, but V bar is of geometric origin. And this is reminiscent of the Fontaine-Laser conjecture, which was already mentioned, I think, in this conference. But you see that here there is no local condition at P, so there is no Durham condition, and this is due to a very striking and result due to Troff, who showed that under the irreducibility condition, in fact, the fact that V bar is Durham is automatic, that V is Durham is automatic. And well, this is wide open, even wider open than the Tate conjecture itself, I would say. But at least it is known in one case, which is very nice. This is a recent result by Jos Lam and Daniel Litt, that this is true for rank 2 local systems on X, which is P1 minus 4 points. And the reason that it is known in this case is that, in fact, such local system can all be described with help of an algorithm, which is called the middle convolution algorithm, which was devised by Nick Katz. And they are all obtained through this middle convolution algorithm from other rank 2 local systems, but on the elliptic curve, which is a double cover branch of P1 branch at it. And you look at rank 1 system on the elliptic curve, you project on P1, this gives you a rank 2 system. But since this rank 2 local system come from rank 1 local systems, they are easy to classify and to study, and one can prove in this that they come from geometry. In fact, under these conditions, they are just torsion. And so this, up to my knowledge, this is the only known case of this very nice Anabelian or variational, if you like, analog of the Tate conjecture. And well, that's all I have to say, I think. Thank you.